Mr. Ryan, are you right?
Yeah.
Look, so we got a few numbers here. So each number represents the number of candies, right? Or bananas, okay? The number of bananas for each pie. Okay, so let's play a game, right? Look at this. There are 1 banana, 3 bananas, 2 bananas, 6 bananas in a row. So you play and I play this game. Your turn first. You can pick.
6 bananas, yum.
Yeah, you can pick the bananas from the front or the back at each time. And I got to pick next. So you pick first, I pick next, and then you pick, I pick. So we take turns, right? So can you win no matter how I play? So put it this way. So you and I both play optimally, right? So can you always win for this one? So what's your strategy?
I take the biggest number.
Okay, you pick 6, yeah? You pick 6 and then I pick, I can pick 2, right? You pick 6, I pick 2. And then
I pick 3.
you pick 3 and I pick 1. Yes, no matter. You because you pick first. You pick 6. If I pick 1, you can pick 3, right? You always win. But for this one, you get to pick. Can you win?
That depends on who starts first.
You always start first. That's a good question. You always start first. Can you win?
No, I said that depends on who starts first.
I see. So I mean, in this game, you pick first. So can you win?
No.
No, right? Because you pick 1, I pick 10. You pick this one, I pick 10, right? Yeah. So the question is that we're given a row of bananas, and you get to pick first, and I get to pick next. So each one take turn. So we both play optimally. Optimally, yeah. Please look, optimally. So we want to find out if you can always win, no matter how good I am. Okay.
You get a dictionary and write down how many you scored.
Okay, that's a good one.
Dictionary.
Dictionary. So what's to do with the dictionary?
You write down your scores.
Yeah, okay, so we use the dictionary to write down the score. Okay, so what's the strategy? I mean, always pick the biggest in the front or in the end, right?
Mm-hmm.
It's not always, I mean, this question is not about how to find the maximum, right? It's not about how finding the maximum score. It's about winning, right? At each turn, if you get to play, you have 2 choices. You pick in the front or in the back, right? You only have 2 choices. So we can brute force, right? Alright. So, for example, if I were you, I were you, yeah. I got to pick, right? I got to pick this one or this one. So I only have 2 choices, right? So I can brute force this. If I pick this one, then I have a smaller size of problem. If I pick this one, I have a smaller size of problem. And which one is bigger? Right? Which one is bigger? I always pick the one which gives me the most advantage. Right? And then this advantage, if it's more than you. This is like a 2-player zero-sum game, right? 2-player. I pick 1 score. I'm trying to maximize the numbers I pick. And then you're trying to minimize. Yeah, we talk about that, the min-max game. Min-max. Right, so this game 3, right? Remember?
Mm-hmm.
So at here, I'm trying to maximize 2 and 3, right? And your turn is trying to minimize. And then maximize, minimize, maximize, minimize. Each turn, 2-player, right? I'm trying to maximize this. You're trying to minimize this. Okay, so look, this is all positive, positive numbers. So I'm trying to maximize, so I can add numbers. You're trying to minimize, and you can subtract. So who will win? If I'm winning, so the sum would be positive, am I right? Yeah, look, if I pick 6 and you pick 7, 6 minus 7 smaller than 0, you win. If I pick 6, you pick 2, the difference would be 4, and I'm winning. So we're just trying to compute the sum, right? I'm trying to maximize, I'm trying to add the numbers. You're trying to subtract the numbers. And then if the sum is positive, I'm winning. If the sum is negative, you're winning, right?
Yes.
So we talk about the min-max. Yeah, min-max function. We can have this. We have this turn, right? Turn. Whose turn is it? And then we want to give a range from 2, right? I and j, right? I and j means that the subarray. Whose turn is it on the subarray? And this return the score. This is score. If it's bigger than 0, I'm winning. If it's smaller than 0, you're winning, right? But since this is a two-player game, so if I'm adding this number, you are subtracting this number, we can get rid of this term, right? We just have to subtract in it. So to put it this way, let's define the function. Define Fij, right? Look, P equals this array, right? Fij means that start from the index I up to index j inclusive. So we want to find out the score as I am picking, right? If this function returns a positive number, then I'm winning. If it's a negative number, you're winning, right? Remember that, right? So look, if I equal j, we're trying to prove something at this point. If I equal j, so if only number, so what should we return? Just return itself, right? At this point, I'm picking, right? Look, there are 3 bananas here. My turn. So what would you do? Pick it.
Yeah.
Just 3. So return Pi, right? Or Pj, doesn't matter. We have 2 choices, right? So we have 2 choices. We want to pick the maximum. We just return maximum. Maximum or what? Look, if I'm picking the left, right? Picking the left, so it's Pi. This is the number I pick. And then the next you picking, right? You're picking. So you pick the numbers from the I plus 1 to j, right? Because I already picked the I here, right? It's minus, look, Fi plus 1, j. Pi, this is the bananas. If I pick the leftmost, right? And then your turn is Fi plus 1, j. But you have to neglect this. Remember, I'm trying to maximize, you're trying to minimize, right? This is the subtract here. And the other way, if I pick this one, right? Look, if pick the rightmost, so that's Pj, F minus, can you give me this? Look, I pick the rightmost, so what's left?
I to j minus 1.
We're done. I to j minus 1. And then I just have to say, look, return F0 from 0 to length of the P minus 1. This is the score, right? And if I'm winning, if I can always win, so this number needs to be bigger than 0 or smaller than 0.
Bigger.
Bigger than 0. We're done. Yeah. What's missing? Look, what's missing?
Cash.
We're done. If I don't put a cash, that's a true false. Yeah. Every time I have 2 choices, pick the left or pick the right, right? And then we just make it a smaller problem by recursion. But that's going to take ages because some of these sub problems might be calculated over and over again. If I put a cache means that I want this f function to be remembered, the values to be remembered as long as we have it. Right? So look, I is from 0 to n minus 1. J is from 0 to n minus 1. So for I, there are n choice. For j, there are n choice. So altogether is n times n. So we have n squared state because we put a cache. So the time complexity is O(n) squared. The space complexity O(n) squared, right? We're putting in cache. This is basically top-down dynamic programming. We talk about it, right? Remember the recursion with the minimization. It's basically a top-down. So we given this f0, for example, f0, let's say 10, okay? Now in order to calculate f0 10, you will calculate p0 minus f1 10 and p10 minus f1 9, right? Which one is the maximum? Get the maximum. Or, right, you'll calculate this value, right? Yeah? Because in order to get f0 10, you need these 2 values. And look, f1 10, again, you need 2 values. f1 9, again, you need 2 values. So this is the search tree. This is the search tree, right? F function is basically a search tree. Every time it has 2 values, you will calculate 2 values. And some of these values may be calculated over and over again. So that's why we have this cache function. To remember it once we have it. This is like Fibonacci number. When we calculate this value, we store it using the notebook cache. Remember it. So basically saying that, okay, let's say somehow f34, I have calculated again. The first time, okay, the value is 5, and I put down in the notebook. The notebook, right? Notebook. So the next time, okay, I need the f34 value again. I look it up. It's there. Then I just return instead of calling this function recursively to do it. Do you get it? Yeah. This is top down. We can convert it to bottom up, right? We can convert it to using the arrays, two-dimensional arrays to store it. So we can do this. We can do this. Okay. This is the same. So dp value n. We know this n. Yeah. N equals length p. dp equals 0 times n for this is a two-dimensional array, or for underscore in range n. For I, we need to initialize the value. For I in range n, dp I, right? dp I equals pi, right? Look, dp I equals pi because if I equals j, if we have only one number, if we only have one pile of banana, we just take it. We will just rather take it, right? Yeah? You're not allowed to skip, by the way. Okay. Yeah? This 1, 10, 1. Then you can just go, you go first. Then I will say, okay, you go first. Nobody will start picking. So dpii, if from I to I, a single pile of bananas, we just pick it. Return it. Okay. For I in range, start from the right. So I will go this way. I will go this way. So we start the index I this way. And then j will start from here. Okay, from I to the n. So for I in range n minus 2 to minus 1, minus 1, we start from the second to the last index backwards. And for j in range I plus 1 to the n, right? So now we just have to do this. Yeah. So dp ij equals, so basically is this the same. pi minus dpi plus 1j, or pj minus dpij minus 1. So this expression is the same, and then at the end we just return dp from the 0 to the minus 1. So meaning that this is we are given this the entire pile of some bananas. We want to find out the score if it's bigger than 0, right? Yeah. So the left one is the top-down dynamic programming. This is done by recursion with minimization. The right one is the bottom-up dynamic programming. Yeah. Look, we're storing the values in the DP array, and then we can compute the values ourselves. Right? So the time complexity and space complexities for both implementations are the same, but practically speaking, the one on the right, the bottom up, is generally faster because we don't have this overhead of calling the recursion. Okay, yeah. Okay, so what have you learned today? Right, what have you learned today? Come on.
About game.
A game. Okay, so
Picking whatever.
what algorithm are we using? So what's the problem? What's the picking the apples and how do we solve it?
There's some piles of blah blah.
Yeah,
Whatever.
bananas.
Candies, candles, bananas, apples, pears,
Yeah.
water bottled seeds.
Okay, and then what are we doing? So each turn we can pick. We have two choices: pick the front and pick the right, right? Pick the back.
And you want to find out how you could win.
You can always win, right?
No matter what.
No matter your opponent.
And you can't skip.
You can, yeah, your opponent can skip. Both players can skip, and both players play ultimately, right? Ultimately. So we want to find out that. And
We're using dynamic programming.
dynamic programming. Fij means that we want to find out the score. Because I'm trying to maximize. You're trying to minimize. It's a min-max tree. Right? It's a min-max tree. If this score is bigger than 0, then I'm winning. If it's smaller than 0, then you're winning, right? So to calculate this function, we need to find out the maximum of these two values. So the first one, pi minus fi plus 1j, basically meaning that if I pick the first one, then that's the remaining. If you pick the last one, that's the remaining. And then we put a negative sign because the next player, right? I'm maximized, and then you're minimized. You're subtracting, right? Right? So look, 1 negate will be minus 1, and negate that will be 1, right? So every time you cause the recursion, the min-max tree, the sign will be negative. And that's just like 2 players playing. I'm trying to maximizing, you're trying to minimizing, and then my turn maximizing again, and your turn minimizing again. Okay? And then if this score is bigger than 0, then great, I'm winning. If it's smaller than 0, then you're winning. And if it's equal to 0, then that's a draw, right? Yeah. If it's equal to 0, this function is return 0, then it means that you're not always winning. Okay. That will be for today. Good job. Bye bye.
Bye.
Bye bye.